A battery cell built in a lab in Dalian just survived 350 full charge cycles while holding on to 84% of its original capacity. A separate Chinese company strapped its battery to a nail and drove it straight through the casing on purpose. It did not catch fire. It did not explode. That is not a lab curiosity. That is a solid-state battery, and China just put a date on when it shows up in your driveway. Here is what makes this genuinely interesting. The gap between this battery and the one sitting in a Tesla or a BYD Seal right now is not a small efficiency bump. It is the difference between a battery that needs a flammable liquid to function and one that does not need that liquid at all. Remove the liquid and you remove the single biggest constraint that has limited electric vehicles since the very first one rolled off a line. If you enjoy videos that break down what is actually happening inside Chinese technology before it hits the mainstream, hit like and subscribe so you never miss one. Now let's get into how a piece of ceramic and a piece of metal almost ended the EV range war. The 500-kilometer ceiling nobody could crack for more than a decade, the entire electric vehicle industry has run on one chemistry, lithium-ion, with a liquid electrolyte ferrying charged particles back and forth between two electrodes. Tesla built an empire on it. CATL became the largest battery maker on Earth refining it. BYD scaled it into the cheapest EVs ever mass-produced. These are not small achievements. The engineers who pushed liquid lithium-ion from a niche laptop battery into something that can move a 2-ton SUV 500 kilometers deserve real credit. But liquid lithium-ion has a ceiling, and the industry has known about it the entire time. The liquid electrolyte inside every one of these batteries is a flammable organic solvent. Push the energy density higher, charge it faster, or damage the casing in a crash, and that liquid becomes the failure point. Battery fires are rare, but they are catastrophic when they happen, and they happen because of the liquid. There was also a quieter cost nobody liked to say out loud: range. Even the best mainstream EV batteries top out around 250 to 300 watt-hours per kilogram. That ceiling is not a marketing problem. It is a chemistry problem. You can refine the manufacturing, tweak the cathode chemistry, add more cells, but you cannot escape what liquid electrolyte fundamentally allows. And while the established battery giants were busy refining that same liquid chemistry for the 15th straight year, a handful of Chinese research institutes and battery startups were busy trying to remove the liquid completely. What happens when you take the liquid out? The most counterintuitive part of a solid-state battery is this. Getting rid of the liquid should make everything simpler, but it almost broke the entire technology. Replacing a liquid electrolyte with a solid one sounds like swapping one ingredient for another. It is closer to performing surgery on the battery's entire internal architecture. Think of the old liquid electrolyte as a river. It surrounds both electrodes completely, filling every gap and crevice, so lithium ions can flow freely, no matter how uneven the electrode surface is. A solid electrolyte cannot do that. It is rigid. The reference scripts in this space describe it the way Chinese researchers themselves describe it, pressing a piece of modeling clay onto a ceramic plate. The clay is the soft lithium metal electrode. The ceramic is the brittle solid electrolyte. Press them together and the contact point is full of microscopic gaps and pits. Because rigid materials do not conform to each other the way a liquid does, that gap is not cosmetic. It is the reason solid-state batteries have spent almost 20 years stuck in laboratories instead of cars. Poor contact between electrode and electrolyte chokes the flow of lithium ions, kills charging speed, and shortens the life of the cell with every cycle. This year, multiple Chinese teams cracked that exact problem, and they did it from 3 different angles. A team at the Institute of Physics at the Chinese Academy of Sciences engineered what researchers are calling a self-migrating interface material, a compound that automatically moves toward the gap between electrode and electrolyte while the battery is operating, filling in the pits as they form instead of trying to prevent them in the first place. Researchers at the Dalian Institute of Chemical Physics took a different route, building a composite electrolyte out of polyvinylidene fluoride and lithium oxychloride that held 84% of its capacity after 350 charge cycles in lab testing. Greater Bay Technology, backed by automaker GAC, built a proprietary deep eutectic composite electrolyte and rolled out actual A-sample cells, not lab coin cells, but full-format cells meant for real vehicle integration, that is, Flip 1. For nearly 2 decades, the assumption was that solid-state batteries were blocked by chemistry, that lithium metal anodes themselves were simply too unstable to scale. The actual blocker was never the chemistry of the materials individually, it was the physical contact between them. Once Chinese labs treated that interface as the engineering problem to solve rather than the chemistry, progress moved fast. The numbers back it up. Today's best mainstream EV batteries deliver roughly 250 to 300 watt-hours per kilogram. Greater Bay Technology's new A-sample cells are hitting 260 to 500 watt-hours per kilogram, nearly double the upper end of what is currently on the road. FAW Group installed a semi-solid-state battery pack with a cell energy density above 500 watt-hours per kilogram into a real vehicle, with a 142 kilowatt-hour pack rated for more than 1,000 kilometers of range under China's CLTC testing cycle. That is not a marginal gain. That is the difference between an EV that needs a midday charging stop on a long drive and one that does not. That is not a metaphor, that is just the math. A 500 kilometers battery gets you from one major city to the next with room to spare. A 1,000 kilometers battery gets you across an entire country. The cells that already passed the nail test lab numbers are easy to announce. Real-world validation is harder to fake, and that is exactly where this story moves from promising to credible. Greater Bay Technology's facility sits in Guangzhou's Nansha district, and it is not a research bench, it is a manufacturing base being scaled toward gigawatt-hour level output before the end of 2026. The company has already filed more than 50 patents covering both the electrolyte chemistry and the manufacturing process around it, which is the kind of detail that separates a real production push from a press release. Here is the test that actually matters. Greater Bay Technology's solid-state cells went through nail penetration testing and thermal shock testing, the two standard torture tests used to simulate a battery getting punctured or overheated in a real crash. A liquid lithium-ion cell that fails these tests catches fire or vents toxic gas, sometimes within seconds. These solid-state cells did neither. They sat there with a nail driven straight through the casing and stayed inert. The performance data lines up with the safety data. FAW's installed pack delivers more than 1,000 kilometers of CLTC range from a 142 kilowatt-hour pack. Dongfeng Motors has been road testing a solid-state prototype through cold weather conditions specifically, since low temperatures are historically where battery performance collapses the fastest, and its pack rated at 350 watt-hours per kilogram is also clearing the 1,000 kilometer mark. Compare that to where mainstream EVs sit today. The best long-range Tesla Model S currently tops out around 600 to 601 obols of real-world range. China's solid-state prototypes are already running 50 to 65% further than that in vehicles that are not yet even in showrooms. The decision signal here matters more than any single number. China's National Automotive Standardization Technical Committee released the first formal draft of a solid-state EV battery standard late last year, opened it for public comment through February, and is on track to finalize and publish that national standard in July 2026. Governments do not write national technical standards for battery chemistries. They expect to stay in the lab. A standard is the bureaucratic equivalent of a green light. It exists because regulators expect these batteries on public roads soon enough that classification, testing protocols, and safety certification need to be settled in advance. That signal is showing up across the supply chain too. BYD is developing its own sulfide-based solid-state cells using high-nickel cathodes paired with silicon-based anodes, targeting roughly 400 watt-hours per kilogram and up to 10,000 charge cycles. For context, a typical liquid lithium-ion EV battery is usually rated for somewhere between 1,000 and 2,000 cycles before meaningful degradation. BYD is not treating this as a side project either. The company is expanding a dedicated oxide-based battery production line in Chongqing with a planned 20 gigawatt-hour capacity, sized specifically to support solid-state demonstration vehicles before a wider rollout closer to 2030. That is not a small efficiency gain stacked onto an existing product line. That is multiple competing Chinese manufacturers, GBT, FAW, Dongfeng, BYD, independently racing toward the same destination using different chemistries, which is usually the strongest sign an entire industry believes a technology shift is real and not hype. Why this is bigger than one battery pack. Once you zoom out from any single company's roadmap, the competitive response becomes the real story. Goshen High-Tech has announced plans to begin production in 2026 with a pilot deployment targeted for 2027. Toyota, watching from Japan, is aiming for 450 to 500 watt-hours per kilogram, but is not expecting even small-scale production until 2027 to 2027, to 4 year or more behind where Chinese manufacturers are already sitting. Samsung SDI is promising an 80% charge in 9 minutes by 2027. In the United States, Factorial Energy partnered with Mercedes to push a modified EQS to 1,205 kilometers on a single charge using solid-state cells, and has since launched a passenger vehicle program with Karma Automotive, proof that Western players know exactly what is at stake and are scrambling to keep pace. This is not about national pride or who gets to claim the technological flag first. It is about math. A solid-state battery pack that delivers double the energy density at a similar weight changes the calculus for every automaker's vehicle architecture, every charging network's business model, and every government's electrification subsidy strategy. Automakers that are still optimizing liquid lithium-ion in 2027 will be optimizing a chemistry that the market has already started moving past. That is not ideology, that is staying in business. Here is the scale math payoff. If solid-state batteries hit their 2027 demonstration targets and reach the 1,000-plus kilometer range multiple Chinese manufacturers are now reporting in prototype testing, a single charge would carry a vehicle roughly the distance from Beijing to Shanghai or from Los Angeles to the Oregon border without stopping. A conventional gas car with a full tank typically covers 600 to 800 kilometers. For the first time, the electric option would not just match that number, it would beat it. That is Flip 2. The original framing of the solid-state battery race was that it would simply close the gap between EVs and gas cars, give electric vehicles enough range to stop worrying about it. The actual implication is bigger and more permanent than that. Once solid-state batteries clear the 1,000-kilometer mark at competitive cost, the range advantage flips entirely in favor of electric vehicles. Gas cars do not have a credible path to matching that number. The entire decades-long argument for keeping a gas car as a backup, long road trips, no charging infrastructure, cold weather performance, starts to disappear as one objection at a time. It is worth being honest about the obstacles because they are real. Say ATL, the largest battery maker in the world and the company with the most to gain or lose, has repeatedly said large-scale commercialization is unlikely before 2030. Battery scientist Ouyang Minggao has publicly predicted solid-state batteries will capture as little as 1% of the market within a decade. Manufacturing solid electrolytes at automotive scale, with consistent quality across millions of cells, is a genuinely different problem than building a few hundred A-sample cells in a controlled facility. The interface contact problem that took 20 years to partially solve in the lab still needs to survive a stamping press, a hot summer, and a teenager's first fender bender. But the pattern here is one that has played out before. Kodak invented the digital camera sensor and shelved it to protect film sales. Nokia had a touchscreen smartphone prototype years before the iPhone and never shipped it. In both cases, the company that owned the old technology was not technically wrong about the new technology being unready. They were wrong about how fast unready turns into unstoppable. China's solid-state push is not waiting for the technology to be perfect before building factories around it. It is building the factories now while the technology is still being finished, which is exactly the opposite of what Kodak and Nokia did. The standard the whole industry will be measured against solid-state batteries are no longer a laboratory curiosity. That is the verdict, stated plainly, without hedging. What started as a chemistry problem that stumped researchers for 2 decades has, in the span of a single year, turned into a manufacturing race with real factories, real production targets, and a real government standard arriving in July 2026. What this new standard actually measures matters more than the headline number. China's National Automotive Standardization Technical Committee is not simply rubber stamping a marketing term. The draft standard Solid-State Battery for Electric Vehicle Part 1 Terms and Classification exists to draw a hard line between genuine all-solid-state cells and the semi-solid or hybrid packs that blend a small amount of liquid electrolyte with solid components as a bridge technology. That distinction is not bureaucratic nitpicking. It is the difference between a battery that has fully solved the interface contact problem and one that is still leaning on a few percentage points of liquid to paper over the gaps. The committee released that first draft in December, ran the public comment period through late February, and is now moving through final review ahead of a planned April decision, with formal publication targeted for July 2026. Once that standard is finalized, every Chinese manufacturer claiming solid state will have to prove it against a fixed technical definition. That is exactly the kind of regulatory clarity that turns a hype cycle into an actual industry, because it strips away the ability of any company to call a 5% liquid hybrid pack a true solid-state battery just to win headlines. Here is the window statement, and it is a narrow one. Greater Bay Technology is targeting gigawatt-hour scale production by late 2026, with cells debuting in GAC's HipTech lineup. FAW and Dongfeng already have semi-solid and hybrid packs installed in test vehicles, clearing 1,000 kilometers of CLTC range today, not in some projected future. BYD's 20 gigawatt-hour Chongqing line is sized for demonstration vehicle integration before 2030. Goshen is targeting pilot deployment in 2027. Toyota is not expecting even small-scale production until 2027 to 2028 at the earliest, and Samsung SDI is still chasing a 9-minute fast charge target it hopes to hit by 2027. That 18 to 24-month gap between Chinese pilot production and Western pilot production does not sound enormous on paper. In an industry where a single battery generation can define which automaker dominates a decade of sales, it is the entire ballgame. Think about what actually happens during that gap. While Western automakers are still finalizing lab-scale demonstrations, Chinese manufacturers will already be running production lines, training factory workers on solid electrolyte handling, refining yield rates, and signing long-term supply contracts for lithium metal anode material. Manufacturing know-how does not transfer instantly once a competitor decides to catch up. It compounds, the same way it did for liquid lithium-ion battery production over the last 15 years, when Chinese manufacturers like CATL and BYD scaled so far ahead on cost and yield that Western and Japanese automakers spent a decade trying to claw back ground they never fully recovered. The company's tooling factory lines around solid-state chemistry right now will own the manufacturing know-how, the supply chain relationships for lithium metal anodes and solid electrolyte materials, and the patent portfolios, more than 50 from Greater Bay Technology alone, before competitors have finished their first small batch production run. Patents matter here in a very specific way. They are not just legal protection. They are a map of where the hardest engineering problems were actually solved, and right now that map is overwhelmingly being drawn in Chinese research institutes and Chinese factories. The deeper reframe is this: every major energy storage transition in the last century has rewarded whoever solved the unglamorous engineering problem first, not whoever had the better idea on a whiteboard. The idea of a solid electrolyte replacing a flammable liquid one is not new. Researchers have chased it since the 1990s, and dozens of academic papers proposed versions of it decades before any company built a working cell. What changed in the last 12 months was not the concept. It was the boring, granular work of getting a piece of ceramic and a piece of metal to actually touch each other cleanly at a microscopic level, millions of times without degrading. That is not a flashy breakthrough. There is no dramatic unveiling, no stage presentation, no viral demo video. It is the kind of unglamorous material science that rarely makes headlines, buried in interface chemistry papers and patent filings most people will never read. And it is precisely the kind of problem that determines who manufactures the next era of vehicles and who spends the 2030s playing catch-up. The country that solves the boring problem first usually ends up writing the rules for everyone else. The same way the country that solved lithium-ion manufacturing at scale ended up controlling most of the world's battery supply chain for the last decade. It is also worth sitting with what this means beyond the spec sheet. A battery is not just a component. It is the single piece of technology that has defined more than any other what an electric vehicle can and cannot do. Every conversation about range anxiety, every debate about whether EVs are ready for road trips, every argument about cold weather performance traces back to the same limiting chemistry. Solve that limitation at the interface level, and you are not just improving a product, you are removing the last credible argument for keeping a gas car as a backup vehicle. If this video helped you understand what is actually happening inside the Chinese EV battery race instead of just the headline version, that is exactly the kind of breakdown this channel exists to do. Hit like and subscribe so you catch the next one, because this story is moving fast enough that the numbers in this video may already be outdated within a year. We want to hear your take in the comments. If solid-state batteries do hit 1,000 plus kilometers of real-world range at a competitive price within the next 3 to 4 years, do you think gas-powered cars become a hobbyist niche the way film cameras did? Or is the global fueling and service infrastructure too deeply embedded for that shift to happen quickly, even with a clearly superior battery? There is no wrong answer. Let's talk about it below.